Hello there, and welcome to The Sleepy Astronaut, where mysteries from the depths of space meet the gentle embrace of slumber. Tonight, we're embarking on a fascinating journey to explore something truly extraordinary that's currently making its way through our solar system. A visitor from another star system entirely that has astronomers both excited and just a little bit curious about what it might mean for our cosmic neighborhood. Before we begin our exploration of this remarkable celestial wanderer, I'd love to know where in the world you're drifting off to sleep tonight, and what thoughts about the cosmos occupy your mind as you settle in for rest. There's something wonderfully comforting about knowing that while we sleep, the universe continues its ancient dance with objects traveling impossible distances through the cold void, between stars eventually finding their way to our little corner of the galaxy. If you find this cosmic voyage soothing or intriguing or simply a perfect companion for your evening wind down, I'd be deeply grateful if you gave the video a gentle like and perhaps subscribed it. Helps this little sanctuary of space science reach other stargazers who might need a peaceful pause in their day. Now, I do hope this isn't so captivating that it keeps you awake, but if it does well, at least you'll have learned something remarkable about our universe before you drift off into dreams of distant stars and wandering comets. So settle back, slow your breathing, and let's begin our journey. Because somewhere in the vast darkness between here and there, between now and eternity, travels a story that began in another solar system long before Earth was even formed. On a warm summer evening in July 2025, astronomers working with the Atlas Survey telescope in the high desert of Chile made a discovery that would send ripples of excitement through the global scientific community. They spotted something moving against the background of stars, something that shouldn't have been there according to the usual patterns of our solar system. At first glance, it appeared to be just another asteroid, or perhaps a comet, making its routine journey around the sun. But as more observations poured in from telescopes around the world, a remarkable truth began to emerge. This wasn't a local resident of our solar system at all. It was something far more extraordinary. A visitor from the depths of interstellar space, traveling at speeds that defied the gentle orbital mechanics of our familiar celestial neighbors. The object was designated 3I Atlas, marking it as the third confirmed interstellar object ever discovered passing through our solar system. The I stands for interstellar, a classification reserved for these most rare and precious cosmic wanderers that have somehow escaped the gravitational embrace of their birth systems and embarked on journeys measured not in years or decades, but in millions or perhaps billions of years, drifting through the cold, empty spaces between the stars. To understand just how remarkable this discovery is, we need to step back and consider the sheer vastness of interstellar space. Imagine, if you will, the space between stars as an ocean so vast that our entire solar system would be like a small pond, while the nearest star would be another pond thousands of miles away across this cosmic ocean. Objects like 3I Atlas travel in solitude, carrying with them the chemical signatures and physical characteristics of alien worlds we may never visit. Before 2017, we had no direct evidence that such objects regularly visited our solar system. We theorized about them. We modeled their possible trajectories, but we had never actually seen one. Then came Oumuamua, the first confirmed interstellar visitor, a strange elongated object that puzzled astronomers with its unusual acceleration and mysterious composition. It was followed by 2I Borisov in 2019, a more traditional-looking comet that behaved much as we expected a comet to behave. Now, 3I Atlas represents our third confirmed encounter with these cosmic messengers, and perhaps our best opportunity yet to study an object that formed around another star. The implications are staggering. This is material that condensed from the disk around a distant sun. Perhaps when our own solar system was still a swirling cloud of gas and dust. Perhaps even earlier when the universe itself was younger and different from the cosmos we know today. What makes 3I Atlas particularly fascinating is its current trajectory through our solar system. Unlike its predecessors, this interstellar visitor is following a path that will bring it remarkably close to several of our planets. Most notably, Mars, the red planet that has captured human imagination for centuries and continues to be explored by rovers and orbiters from Earth. As 3I Atlas speeds through our solar system at the staggering velocity of over 130,000 miles per hour, it carries with it secrets from its origin world. We know it came from the general direction of the constellation, Sagittarius, the same direction as the center of our galaxy, where hundreds of billions of stars create their own solar systems with their own planets and their own stories of formation and evolution. The comet for that is what 3I Atlas appears to be, is currently passing through the asteroid belt, that rocky debris field between Mars and Jupiter, where countless fragments left over from the formation of our solar system continue their eternal orbits. But 3I Atlas doesn't belong to this ancient debris field. It's an interloper, a stranger passing through, carrying ice and dust that formed under an alien sun. Observations from the Hubble Space Telescope have revealed that 3I-ATLAS displays all the classic characteristics of an active comet as it approaches our Sun. Its icy nucleus begins to warm and sublimate, transforming directly from solid ice to vapor in the vacuum of space. This process creates the distinctive coma, the bright fuzzy envelope of gas and dust that surrounds the comet's solid core, making it visible to our telescopes across the vast distances of space. The spectroscopic analysis of this coma has already revealed the presence of familiar molecules: water vapor, carbon dioxide, carbon monoxide, and other compounds that we associate with comets from our own solar system. This similarity suggests something profound about the universe itself, that the basic chemistry of comet formation may be universal, a process that occurs around stars throughout our galaxy, creating these wandering repositories of primordial ice and dust. But 3I Atlas is not just another comet, it's a time capsule from another world, a fossil record of conditions that existed in a distant solar system, possibly billions of years ago. When it was ejected from its birth system, it began a journey through the galaxy that has lasted longer than complex life has existed on Earth. It has witnessed the slow rotation of spiral arms, the birth and death of stars, the gradual evolution of our entire galactic neighborhood. Size estimates suggest that 3I Atlas is substantial, with a nucleus that may be several miles across, making it potentially the largest of the 3 confirmed interstellar objects we've discovered. This size, combined with its active cometary behavior, makes it an ideal target for detailed study using every tool in our astronomical arsenal. As October approaches 3I Atlas will reach its closest point to the Sun at a distance of about 130 million miles just inside the orbit of Mars. But before that moment arrives on October 3rd, it will pass within 18 million miles of the red planet itself, closer than Mars ever comes to Earth, providing an unprecedented opportunity for the spacecraft currently exploring Mars to observe an interstellar visitor up close. The European Space Agency's Mars Express orbiter and the ExoMars Trace gas orbiter, both equipped with high-resolution cameras and sophisticated spectrometers, will turn their instruments toward 3I Atlas. As it sweeps past Mars, these spacecraft designed to study the red planet will suddenly become interstellar observatories, providing us with detailed images and chemical analysis of this cosmic wanderer from Earth. Multiple ground-based telescopes are tracking 3I Atlas as it brightens steadily with its approach to the Sun. Recent observations suggest it may be brightening more rapidly than expected, a behavior that could indicate increased activity as its nucleus warms, or possibly the exposure of fresh ice as surface layers sublimate away. The James Webb Space Telescope, that marvel of modern engineering currently stationed at the second Lagrange point, has already captured detailed spectra of 3I Atlas, revealing the chemical composition of its coma. With unprecedented precision, these observations provide our first detailed chemical analysis of material from another star system, allowing us to compare the composition of interstellar ice with the comets native to our own solar system. What emerges from these observations is a picture of remarkable similarity. The ice and dust of 3I Atlas appears chemically similar to comets born in our own solar system, suggesting that the processes that create these objects may be universal phenomena occurring around stars throughout the galaxy. This universality implies that the basic chemistry of planetary system formation follows similar patterns regardless of where in the galaxy it occurs. The trajectory of 3I Atlas through our solar system is particularly intriguing because of its alignment with the ecliptic plane. The flat disk in which most of our planets orbit this alignment is statistically unlikely for a randomly oriented interstellar object, leading some researchers to wonder whether this trajectory might be more than mere coincidence. As 3I Atlas continues its journey toward perihelion, its closest approach to the Sun, scheduled for late October, it will reach maximum velocity of nearly 42 miles per second relative to our Sun. This incredible speed is a testament to the gravitational acceleration it receives as it falls toward our star, but it's also a reminder that this is a brief visit after reaching perihelion 3. I-Atlas will begin its journey back into the depths of interstellar space, never to return to our solar system. The rarity of these interstellar encounters makes 3I-Atlas precious beyond measure. We estimate that objects like this pass through our solar system perhaps once every few years, but most go undetected because they're too small or too distant, or simply pointed in the wrong direction for our telescopes to spot them. 3I-ATLAS represents a cosmic lottery ticket, a chance encounter with the unknown that may not come again for years or even decades. But what does this mean for Mars and the planets that 3I Atlas will encounter during its swift passage through our inner solar system? This question has captured the attention of planetary scientists and mission planners who are now scrambling to coordinate the most comprehensive observation campaign ever mounted for an interstellar object. The close approach to Mars on October 3rd presents both opportunities and considerations that extend far beyond simple scientific curiosity. When 3I Atlas sweeps past the red planet at a distance of 18 million miles, it will be moving at such tremendous velocity that any interaction with Martian space environment could potentially have consequences we're only beginning to understand. Mars, unlike Earth, lacks a strong magnetic field to deflect charged particles and cosmic debris. Its thin atmosphere provides little protection from high-speed impacts, and while 3I Atlas itself poses no direct threat to the planet, the dust and gas streaming from its nucleus could interact with Mars' upper atmosphere in ways that might affect ongoing missions. The rovers currently exploring the Martian surface, including NASA's Perseverance and Curiosity, will have front-row seats to this celestial spectacle. Though they won't be able to see 3I-ATLAS directly through the dusty Martian atmosphere, they may be able to detect changes in radiation levels or atmospheric conditions as the comet passes by. More intriguingly, the orbital mechanics of 3I Atlas suggest that it will also make relatively close approaches to Venus and Jupiter, though at greater distances than its Mars encounter. Each of these planetary encounters provides gravitational perturbations that slightly alter the comet's trajectory and velocity, creating a complex dance of celestial mechanics that our computers can model, but nature executes with perfect precision. The dust tail of 3I Atlas, streaming behind it like a gossamer thread, millions of miles long, will sweep across various regions of the solar system as the comet continues its journey. This dust, composed of particles ranging from microscopic grains to pebble-sized chunks, carries the chemical fingerprints of another star system and will eventually disperse throughout our local space environment. Some of this dust may eventually make its way to Earth's atmosphere, years or even decades from now, creating meteors that carry the chemical signatures of an alien world. Imagine standing under a dark sky, watching shooting stars that originated not from our asteroid belt, but from the disk around a distant sun billions of years ago. The speed at which 3I Atlas travels through our solar system, over 60 kilometers per second relative to the sun, means that any collision with even small debris could release enormous amounts of energy equivalent to multiple nuclear weapons. This vulnerability makes the comet's journey through our asteroid-rich inner solar system something of a cosmic game of chance. Astronomers have calculated that there are approximately 1 trillion rocks larger than 20 meters in diameter within the asteroid belt region that 3I Atlas is currently traversing. While the probability of a direct collision remains extremely low, the consequences would be spectacular and potentially observable from Earth as a sudden brightening or even fragmentation of the comet. Such an event would be both scientifically fascinating and somewhat tragic, as it would destroy this irreplaceable messenger from another star system, but it would also create a debris cloud that could be studied for months or years, providing multiple samples of interstellar material scattered across various orbits within our solar system. The question of whether 3I Atlas poses any threat to human activities in space has been carefully considered by space agencies worldwide, while the comet itself will not come anywhere near Earth. Its dust trail and the possibility of fragmentation events create considerations for satellite operations and future space missions. The International Space Station, orbiting at an altitude of roughly 400 kilometers above Earth's surface, remains well protected by our planet's atmosphere and magnetic field. But satellites in higher orbits, particularly those in geosynchronous positions, might experience increased micrometeorite activity as particles from 3I Atlas eventually disperse throughout the inner solar system. More immediate concerns focus on the Mars exploration program, where multiple orbiters and surface missions represent billions of dollars in scientific investment and decades of careful planning. The European Space Agency has issued advisories to mission controllers suggesting enhanced monitoring of spacecraft systems during the period surrounding 3I Atlas, closest approach to Mars. The possibility, however remote, that 3I Atlas might interact gravitationally with Mars. Small moons, Phobos and Deimos, has also been considered. These irregularly shaped satellites already follow precarious orbits around Mars, and any perturbation could potentially alter their trajectories. Though calculations suggest that the gravitational influence of 3I Atlas at its closest approach distance would be negligible. Perhaps more intriguing are the electromagnetic effects that might occur as 3I Atlas ionized coma interacts with the solar wind and planetary magnetic environments. While Mars lacks a global magnetic field, it does possess localized magnetic anomalies, particularly in its southern hemisphere, that could potentially interact with the charged particles streaming from the comet ground-based radio telescopes on Earth are already monitoring for any unusual electromagnetic signatures that might indicate interactions between 3I Atlas and the interplanetary medium. These observations could provide insights into the electrical properties of interstellar comets and how they behave differently from native solar system objects. The timing of 3I Atlas arrival during a period of relatively low solar activity means that the background electromagnetic environment is calmer than it might otherwise be, allowing for more sensitive detection of any subtle effects the comet might produce as it moves through our solar system. Scientists are particularly interested in whether 3I Atlas will exhibit any unusual behavior as it approaches perihelion, its closest point to the Sun. Comets are notoriously unpredictable, and this one carries the additional mystery of having formed under conditions that may have been quite different from those in our own solar system. The chemical composition revealed by spectroscopic analysis shows familiar molecules, but the ratios and isotopic signatures may tell a different story about the stellar environment where 3I Atlas originally formed. If its parent star had different metallicity or age than our Sun, the resulting differences in comet composition could be subtle but scientifically profound. As 3I Atlas continues to brighten, recent observations suggest it may be becoming more active than initially predicted. This increased activity could indicate that its nucleus contains more volatile materials than typical solar system comets, or that its structure is somehow different, allowing for more efficient heat transfer to subsurface ices. The brightening pattern also raises questions about the comet's rotation period and axis orientation factors that affect how evenly solar heating occurs across its surface. A tumbling rotation could create periodic variations in brightness and activity that would be visible from Earth, providing clues about the physical structure of this interstellar wanderer. Mission planners at NASA and ESA are working to coordinate observations from multiple spacecraft positioned throughout the solar system, creating an unprecedented multi-platform study of an interstellar object. The Parker Solar Probe, currently diving close to the Sun, will be positioned to observe 3I Atlas during its most active period near perihelion. The SOHO Solar Observatory, stationed at the first Lagrange point between Earth and the Sun, will monitor the comet as it disappears behind our star and emerges on the other side, potentially capturing images of any dramatic changes in activity level or structure that might occur during its closest solar approach. Even the Juno spacecraft currently orbiting Jupiter may be able to contribute observations of 3I Atlas from its unique vantage point in the outer solar system, providing a different perspective on the comet's coma structure and dust production rates. This coordinated observation campaign represents one of the most ambitious efforts ever undertaken to study a single astronomical object involving ground-based telescopes, space-based observatories, planetary missions, and even citizen scientists around the world, who are contributing their own observations to the growing database of 3I Atlas measurements. The data being collected will not only enhance our understanding of this particular interstellar visitor, but will also inform our preparations for future encounters as detection systems improve, and our ability to spot these rare objects increases. We expect to discover more interstellar visitors in the coming years and decades. The Vera Rubin Observatory, currently undergoing commissioning in Chile, promises to revolutionize our ability to detect and track objects like 3I Atlas. Its massive camera system and automated survey capabilities could potentially discover one interstellar object every few months, rather than the current rate of perhaps one every few years. This dramatic increase in detection capability will transform interstellar objects from rare curiosities into a new class of astronomical phenomena that we can study systematically, comparing their compositions, trajectories, and behaviors to understand the diversity of materials being exchanged between star systems throughout our galaxy. The implications of studying 3I Atlas extend far beyond simple astronomical curiosity into realms that touch the very foundations of how we understand planetary formation and the chemical evolution of our galaxy. When we analyze the light streaming from this comet's coma, we're essentially performing archaeology on a cosmic scale, examining materials that may predate our own solar system by billions of years. Imagine for a moment the journey that 3I Atlas has taken through space while our sun was still forming from a collapsing cloud of gas and dust. This object may have already been wandering between the stars, carrying within its frozen nucleus the chemical signatures of stellar processes that occurred when the universe was younger and different from what we see today. The isotopic ratios found in 3I Atlas could tell us about the nuclear fusion processes occurring in its parent star. The abundance of heavy elements might reveal whether that star was part of an earlier generation of stellar formation, when the galaxy contained fewer of the complex atoms necessary for rocky planet formation. As we drift deeper into this cosmic mystery, it's worth considering what the discovery of 3I Atlas means for our understanding of how common such exchanges might be between star systems throughout our galaxy. Every star system likely ejects material during its formation process: rocky debris, icy planetesimals, and perhaps even larger objects that get flung into interstellar space by gravitational interactions with giant planets. This means that right now, at this very moment, there are probably millions or even billions of objects similar to 3I Atlas, wandering through the space between stars, each one carrying samples of its home system, each one a potential messenger that could arrive in our solar system at any time over the coming millions of years. The realization that we live in a galaxy where star systems regularly exchange material has profound implications for our understanding of how planets form and evolve. It suggests that the building blocks of worlds are not confined to their birth systems, but can travel vast distances carrying complex organic molecules and perhaps even the seeds of life itself from one stellar neighborhood to another. Some scientists have speculated that objects like 3I Atlas could serve as vehicles for panspermia, the hypothetical transfer of life between planets or even between star systems. While this remains highly speculative, the discovery that interstellar objects regularly visit our solar system at least opens the possibility that Earth's biosphere might have received contributions from elsewhere in the galaxy. The organic compounds detected in 3I Atlas coma, including complex carbon-bearing molecules, provide tantalizing hints about the chemistry occurring around other stars. These molecules form through processes we understand well in our own solar system, but finding them in an interstellar visitor confirms that similar chemistry occurs throughout our galactic neighborhood as 3I Atlas continues its approach toward Mars, and eventual rendezvous with the inner solar system. Astronomers are particularly interested in how its behavior might change as it encounters different regions of space. The solar wind that streams outward from our sun carries charged particles and magnetic fields that interact with cometary material in complex ways. When 3I Atlas first entered our solar system, it was traveling through a region where the solar wind is relatively weak and the interplanetary magnetic field is less organized. But as it moves closer to the sun, these environmental factors become increasingly important, potentially affecting how gas and dust escape from the comet's nucleus. The interaction between 3I Atlas and the solar wind could create observable phenomena, similar to what we see with solar system comets, but potentially with subtle differences that reflect its interstellar origin. The magnetic field frozen into the comet's nucleus during its formation around another star might have different characteristics than those found in native solar system objects. These magnetic signatures, if they can be detected and measured, would provide another window into the conditions that existed in the stellar nursery where 3I Atlas was born. Magnetic fields play crucial roles in star and planet formation processes, and any remnant magnetization in the comet could tell us about the magnetic environment of its origin system. The dust streaming from 3I Atlas as it warms under our sun's influence will eventually spread throughout the inner solar system, creating a tenuous but detectable enhancement to the zodiacal dust cloud that already exists from countless generations of solar system comets and asteroids. This interstellar dust will carry chemical and isotopic signatures that distinguish it from native solar system material, potentially allowing future missions to collect and analyze samples of matter that originated around another star without the need for impossible interstellar travel. The European Space Agency's upcoming Comet Interceptor mission, originally designed to study a pristine solar system, COMET is now being considered for potential modifications that could allow it to analyze dust particles from 3I Atlas, though the mission timeline and orbital mechanics make such an encounter challenging. Even more ambitious proposals have suggested the possibility of sending dedicated spacecraft to intercept 3I Atlas during its outbound journey after it passes the Sun and begins its return to interstellar space. Such a mission would face enormous technical challenges given the comet's high velocity, but it would provide humanity's first close-up examination of an object from another star system. The window for such ambitious missions is rapidly closing. As 3I Atlas continues its swift passage through our solar system after its perihelion passage in late October, it will begin accelerating away from the Sun, eventually reaching the same incredible velocities that carried it here from the depths of spaceground-based observations of 3I Atlas have revealed something unexpected about its nuclear structure, unlike many solar system comets, which show evidence of layered composition or regional variations in activity 3. I-Atlas appears remarkably homogeneous in its behavior, suggesting either a very uniform internal structure or perhaps different formation processes than those that created comets in our own system. The rotation period of 3I Atlas, estimated from periodic variations in brightness, appears to be relatively rapid, indicating that despite its long journey through space, it has retained enough structural integrity to spin without flying apart. This stability suggests that interstellar objects might be more robust than previously thought capable of surviving million-year journeys through the harsh environment of space temperature measurements of 3. I-Atlas nucleus reveal that it's warming exactly as expected for an object of its size and composition at its current distance from the Sun. This predictable thermal behavior provides confidence in our models of how interstellar comets should behave as they approach different types of stars. The albedo or reflectivity of 3I Atlas surface appears similar to that of primitive solar system comets, suggesting that the processes that darken and redden cometary surfaces through exposure to cosmic radiation and solar wind particles operate similarly regardless of which star system. The comet calls home, spectroscopic observations have detected subtle variations in the composition of gas and dust being released from different parts of 3I Atlas nucleus. These variations might reflect regional differences in the original accretion process, or could indicate that the comet has experienced some form of thermal processing during its interstellar journey. The discovery that 3I Atlas contains significant amounts of carbon monoxide, a molecule that sublimates at very low temperatures, suggests that parts of its nucleus have remained extremely cold throughout its journey between stars. This finding supports models suggesting that interstellar objects can preserve volatile materials over cosmic timescales as October approaches, and 3I Atlas makes its closest approach to Mars. Mission controllers are preparing for what might be the most intensive observation campaign in the history of interplanetary exploration. Every available instrument on every spacecraft in the vicinity will be pointed toward this cosmic visitor. The data collected during this brief encounter will need to last us potentially decades until another interstellar object makes such a convenient passage through our inner solar system. The rarity of these encounters makes every measurement precious, every spectrum valuable, every image a treasure trove of information about worlds we may never visit beyond the immediate scientific value. 3I Atlas represents something more profound about our place in the galaxy. It reminds us that we are not isolated in space, but part of a vast cosmic community where matter and energy flow between star systems carrying information about distant worlds and alien skies. The gentle dance of gravity that guides 3I Atlas through our solar system follows the same physical laws that govern the motion of planets around distant stars. The chemistry that creates its glowing coma operates according to the same principles that drive molecular formation in stellar nurseries throughout the galaxy. In this sense, 3I Atlas serves as a messenger not just of scientific data, but of cosmic connection. A reminder that despite the vast distances that separate star systems, we are all participants in the same grand story of cosmic evolution, sharing matter and energy across the light years that divide us. As we prepare to witness this interstellar visitor's closest approach to Mars, we stand at a unique moment in human history. Never before have we possessed the technology to study such an object in such detail. Never before have we had spacecraft positioned throughout the solar system, ready to observe and analyze this cosmic wanderer. From multiple perspectives, the measurements and observations collected over the coming weeks will inform our understanding of interstellar objects for generations to come. They will guide the design of future missions, help us interpret observations of similar objects, and perhaps most importantly, expand our perspective on what it means to be citizens of a galaxy where star systems regularly share their treasures with distant neighbors. Whether 3I Atlas represents a threat to Mars or simply an extraordinary opportunity for scientific discovery may depend largely on our definition of threat. While the comet poses no direct physical danger to the red planet or its robotic explorers, it does challenge our understanding of how solar systems interact and evolve over cosmic timescales. The data we collect from 3I Atlas will undoubtedly raise new questions, even as it answers old ones. It will reveal new mysteries about interstellar space and the objects that travel through it. It will inspire new missions and new technologies designed to study these rare but scientifically precious visitors. As the gentle rhythm of cosmic mechanics carries 3I Atlas ever closer to its appointment with Mars, we find ourselves witnesses to an event that connects us directly to the vast community of stars that surrounds us in this quiet moment between discovery and encounter. We can appreciate both the rarity of this opportunity and the profound implications it holds for our understanding of our place in the cosmos. And so, as we drift deeper into this cosmic tale, we find ourselves contemplating not just the mechanics of celestial motion, but the profound questions that 3IATLAS raises about the nature of our galactic neighborhood and, perhaps most intriguingly, what constitutes a threat in the vast theater of space. When we speak of threats from space, our minds naturally turn to catastrophic scenarios, asteroid impacts that could devastate civilizations, or comet collisions that might alter planetary atmospheres. But 3I Atlas presents us with a different kind of consideration altogether, one that operates on timescales and in ways that challenge our conventional understanding of cosmic risk. The very presence of this interstellar wanderer in our solar system represents what scientists call a low-probability, high-impact event. Something so unlikely that we barely considered it possible until very recently, yet so scientifically significant that it fundamentally changes how we think about the space environment around our planets. As 3I Atlas approaches Mars, traveling at velocities that dwarf anything native to our solar system, it carries with it not just ice and rock, but the accumulated effects of its million-year journey through interstellar space. Cosmic radiation has bombarded its surface, creating complex organic molecules through processes we're only beginning to understand. The comet's nucleus, scarred by eons of exposure to high-energy particles and interstellar dust. Impacts may contain materials that have been altered in ways we've never encountered before. These modifications could include exotic isotopes created by cosmic ray bombardment, or organic compounds formed through radiation chemistry in the cold depths of space. When this altered material begins to outgas as 3I Atlas warms near the Sun, it creates a coma composition that, while chemically familiar in its basic components, may contain trace elements and molecular variants that reflect its unique history. The implications of this cosmic chemistry extend beyond simple scientific curiosity into questions about how interstellar material might affect the environments it encounters. Mars, with its thin atmosphere and weak magnetic field, presents a particularly interesting case study for how planets might interact with interstellar visitors, while 3I Atlas will pass at a safe distance of 18 million miles. The trailing edge of its coma could extend far enough to brush against the outermost reaches of Mars' gravitational influence. The Martian atmosphere, already tenuous and constantly being eroded by solar wind, might experience subtle changes as particles from 3I Atlas interact with its upper layers. These interactions could temporarily alter atmospheric chemistry in ways that might be detectable by the sensitive instruments aboard orbiting spacecraft. The Mars Reconnaissance Orbiter, equipped with spectrometers capable of detecting minute changes in atmospheric composition, will be monitoring for any such effects. During the comet's closest approach, these measurements could provide our first direct evidence of how interstellar material influences planetary atmospheres. More intriguingly, the dust grains streaming from 3IATLAS carry electric charges that could interact with Mars' existing electromagnetic environment. While the red planet lacks a global magnetic field, it does possess localized magnetic anomalies that create complex patterns of charged particle behavior in its vicinity. These magnetic field lines could potentially channel some of the charged dust from 3I Atlas towards specific regions of Mars, creating temporary auroral displays or electromagnetic disturbances that might be visible to orbiting cameras. The possibility of witnessing Martian auroras caused by interstellar dust represents one of the more poetic potential outcomes of this cosmic encounter. Ground-based radio telescopes are already listening for any electromagnetic signatures that might indicate interactions between 3I-ATLAS and the interplanetary medium. These observations could reveal how the electrical properties of interstellar comets differ from those born in our solar system. The timing of 3I Atlas passage through our solar system coincides with a period of relatively low solar activity, meaning that the background electromagnetic environment is calmer than usual. This quieter cosmic weather provides an ideal opportunity to detect subtle effects that might otherwise be masked by solar storms or coronal mass ejections. As the comet continues its inward journey, astronomers have noticed something particularly intriguing about its behavior. The rate at which 3I Atlas is brightening suggests that its nucleus may be more active than initially predicted. This increased activity could indicate several possibilities, each with different implications for our understanding of interstellar objects. One explanation for the enhanced brightness involves the gradual exposure of fresh ice as surface layers sublimate away. If 3I Atlas has spent millions of years developing a dark radiation processed crust, the warming effects of our Sun might be penetrating through this layer to reach pristine ice beneath. Alternatively, the comet's internal structure might be more porous than typical solar system comets, allowing heat to penetrate more efficiently into its interior. This structural difference could reflect formation processes that occurred around its parent star under conditions quite different from those in our own stellar neighborhood. The brightening pattern also reveals information about 3I Atlas rotation and orientation as it tumbles through space. Different faces of its nucleus receive varying amounts of solar heating, creating periodic fluctuations in activity level. These variations provide clues about the comet's shape and surface properties. Observations from multiple telescopes tracking these brightness changes have revealed that 3I Atlas appears to have a relatively rapid rotation period, suggesting that despite its long journey through space, it has maintained structural integrity sufficient to spin without fragmenting. This stability implies that interstellar objects might be more robust than previously thought capable of surviving, not just the cold and radiation of interstellar space, but also the thermal stresses of approaching different types of stars during their wandering journeys. The chemical analysis of 3I Atlas coma continues to yield surprises as more sophisticated instruments examine the light streaming from its nucleus. Spectroscopic observations have detected not just the expected water vapor and carbon compounds, but also more complex organic molecules that hint at rich chemistry occurring in its parent system. These organic compounds, including what appear to be carbon chains and ring structures, provide evidence that the basic chemistry necessary for life operates similarly throughout our galaxy. The presence of such molecules in an interstellar visitor suggests that the building blocks of biology may be more widely distributed than we previously imagined. Isotopic analysis of the gas streaming from 3I Atlas reveals subtle differences from solar system norms that could tell us about the nuclear processes occurring in its parent star. If that star had different mass or metallicity than our Sun, the resulting isotopic signatures would be preserved in materials that formed in its planetary disk. These isotopic fingerprints act like a cosmic DNA that could eventually allow us to identify the stellar neighborhood from which 3I Atlas originated, though such analysis requires extremely precise measurements that push our current instruments to their limits. As 3I Atlas approaches its Mars encounter, mission planners have identified several specific phenomena. They hope to observe the possibility of detecting changes in Mars. Upper atmospheric chemistry represents one of the most scientifically valuable potential outcomes. The European Space Agency's Mars Express orbiter will use its OMEGA spectrometer to search for any unusual molecular signatures that might appear in Mars' atmosphere during the comet's passage. These measurements could provide the first direct evidence of how interstellar material influences planetary environments. More dramatic possibilities include the potential for visible effects such as enhanced auroral activity or atmospheric glows caused by the interaction of charged particles from 3I Atlas with Mars' residual magnetic field. While such displays would be subtle compared to Earth's aurora, they would represent a unique cosmic light show. The ExoMars Trace gas orbiter, equipped with highly sensitive cameras, will be monitoring Mars' night side for any unusual luminous phenomena during the period surrounding 3I Atlas. Closest approach, these observations could capture images of interstellar dust interacting with planetary magnetic fields. Ground-based telescopes will simultaneously observe both 3I Atlas and Mars, providing context for any changes detected by the orbiting spacecraft. This coordinated approach ensures that any effects can be properly attributed to the comet's passage rather than other factors. The dust tail of 3I Atlas, now extending millions of miles behind the comet as it warms under solar heating, presents its own set of considerations. While this material poses no direct threat to Mars, it does represent a temporary addition to the solar system's inventory of small particles. Some of this dust will eventually settle into stable orbits around the Sun, joining the existing population of interplanetary particles that create the zodiacal light visible from Earth before dawn. And after sunset, future spacecraft traveling through these regions might encounter dust grains that originated around another star. The possibility that some particles from 3I Atlas might eventually reach Earth's atmosphere years or decades from now raises intriguing questions about how we might detect and study such material. Meteor showers caused by interstellar dust would carry chemical signatures distinct from normal meteoric material. Advanced detection systems currently being developed could potentially identify individual meteor particles of interstellar origin, allowing scientists to collect and analyze samples of matter from another star system without the need for impossible interstellar missions. The trajectory of 3I Atlas through our solar system will also provide valuable information about the gravitational environment of interstellar space. Precise tracking of the comet's path allows astronomers to calculate how its motion has been influenced by encounters with other objects during its journey. These calculations could reveal evidence of close approaches to other stars or massive objects that have subtly altered the comet's trajectory over millions of years. Each gravitational encounter leaves a signature in the object's motion that can be decoded through careful analysis. The fact that 3I Atlas arrived at our solar system with a trajectory so closely aligned with the orbital plane of our planets represents a statistical curiosity that has attracted considerable attention. While such alignment is not impossible, it is sufficiently unlikely to warrant careful consideration. Some researchers have calculated that the probability of a randomly oriented interstellar object arriving with such precise alignment is less than 1%. This statistical rarity has led to speculation about whether the trajectory might reflect something other than pure chance. However, the scientific consensus remains that 3I Atlas is almost certainly a natural object following a trajectory determined by the complex gravitational influences it has experienced during its long journey through space. The apparent coincidence of its alignment may simply reflect the fact that we are more likely to detect interstellar objects that pass through the plane of our solar system. As October approaches and 3I Atlas prepares for its close encounter with Mars, the international space science community is coordinating what may be the most comprehensive observation campaign ever mounted. For a single astronomical object, the James Webb Space Telescope will continue its spectroscopic analysis of the comet's coma, providing detailed chemical information about this interstellar visitor, while the Hubble Space Telescope captures high-resolution images of its nucleus and dust production. The Parker Solar Probe, currently diving close to the Sun, will be positioned to observe 3I Atlas during its most active period near perihelion, potentially capturing images of dramatic changes in the comet's behavior as it reaches maximum solar heating. Coordination between these space-based observatories and ground-based telescopes around the world ensures comprehensive coverage of 3I Atlas behavior throughout its passage through our inner solar system. This multi-platform approach maximizes the scientific return from this rare opportunity. The data collected during 3I Atlas passage will inform our understanding of interstellar objects for generations to come, providing baseline measurements against which future discoveries can be compared. As detection systems improve, we expect to encounter more such visitors. The Vera Rubin Observatory, now beginning its operations, promises to revolutionize our ability to spot these cosmic wanderers. Its automated survey capabilities could potentially discover interstellar objects on a regular basis, transforming them from rare curiosities into a new class of astronomical phenomena. This transformation from rarity to routine observation will fundamentally change how we study interstellar objects, allowing for statistical analysis of their properties and behaviors rather than relying on individual case studies like 3IATLAS. The implications extend beyond pure science into practical considerations for space exploration and planetary defense. As we develop more sensitive detection systems, we will gain earlier warning of approaching interstellar objects, allowing for better preparation and more comprehensive study. Advanced propulsion technologies currently in development could eventually enable dedicated missions to intercept and study interstellar visitors during their passage through our solar system. Such missions would provide humanity's first close-up examination of materials from other star systems. The possibility of collecting physical samples from interstellar objects represents one of the most exciting prospects in planetary science. These samples would contain information about stellar environments and planetary formation processes that occurred billions of years ago in distant parts of our galaxy. As we continue to track 3I Atlas through its approach to Mars, we are reminded that we live in a dynamic galaxy where star systems regularly exchange material across vast distances. This exchange process may be fundamental to how planetary systems evolve and develop over cosmic timescales. The organic molecules detected in 3I Atlas suggest that the chemistry necessary for life may be distributed throughout our galactic neighborhood, carried by wandering objects like this interstellar comet. While we cannot yet determine whether such objects could transport actual living organisms, they certainly carry the chemical building blocks of biology. The study of 3I Atlas also provides insights into the long-term evolution of our own solar system. Billions of years from now, our sun will eject comets and asteroids that will wander through interstellar space, potentially visiting other star systems and carrying samples of Earth and its fellow planets. In this cosmic perspective, 3I Atlas serves as both a visitor from our galactic past and a preview of our solar system's future, a reminder that we are part of a vast community of stellar systems connected by the slow but persistent exchange of matter across the light years. The gentle dance of gravitational forces that guides 3I Atlas through our solar system operates according to the same physical laws that govern planetary motion around distant stars. The chemistry that creates its glowing coma follows the same principles that drive molecular formation in stellar nurseries throughout the galaxy. As this interstellar messenger continues its journey toward Mars, we find ourselves witnesses to an event that connects us directly to the broader cosmic community in which our solar system resides. The measurements and observations we collect will enhance our understanding, not just of this particular visitor, but of the processes that shape planetary systems throughout our galaxy. The approaching encounter with Mars represents more than just a scientific opportunity. It symbolizes humanity's growing capability to study and understand our place in the cosmic order. As our instruments become more sophisticated and our detection methods more sensitive, we are beginning to see the universe as it truly is, a dynamic, interconnected web of matter and energy flowing between star systems, Whether 3I Atlas ultimately proves to pose any form of threat to Mars seems increasingly unlikely, as detailed observations continue to confirm its nature as a typical, though remarkably well-preserved, interstellar comet. The real significance lies not in any immediate danger, but in what this cosmic visitor teaches us about the nature of our galactic environment. The true nature of this cosmic wanderer becomes clearer with each passing observation, revealing not a harbinger of destruction, but something far more profound. A living laboratory that carries within its ancient ice the secrets of stellar chemistry from across the galaxy. As we settle into this gentle revelation, let us explore what 3I/ATLAS teaches us about the delicate interconnections that bind our cosmic neighborhood together. The monitoring stations scattered across Earth have been tracking subtle changes in 3I Atlas behavior as it continues its approach toward the inner solar system. These observations reveal a comet that appears to be following predictable patterns of activity, increasing brightness and gas production as solar heating gradually warms its nucleus from the frigid temperatures of interstellar space. What emerges from this data is a picture of remarkable consistency with our understanding of how comets behave, regardless of their origin. The fundamental physics of ice sublimation and dust entrainment operates the same way. Whether the comet formed 4.5 billion years ago in our own solar system, or condensed from the disk around a distant star in some other corner of the galaxy, this universality of physical processes suggests something profound about the nature of planetary formation throughout our galactic region. The same chemistry that created the building blocks of Earth and Mars appears to operate around other stars, creating similar materials that eventually find their way into wandering objects, like 3I Atlas. The isotopic signatures detected in the comet's outgassing reveal subtle differences that tell us about the stellar environment where it originally formed. These variations are like fingerprints that could eventually allow us to identify not just the general region of the galaxy from which 3I Atlas originated, but potentially even the specific type of star around which it condensed billions of years ago. As the comet continues warming under our sun's influence, astronomers have detected increasingly complex organic molecules streaming from its nucleus. These carbon-bearing compounds, including some that appear to be precursors to biological chemistry, provide evidence that the fundamental ingredients for life may be widely distributed throughout our stellar neighborhood. The presence of these organic molecules in an object that has spent millions of years traveling through the harsh environment of interstellar space demonstrates the remarkable stability of certain chemical bonds under extreme conditions. This stability suggests that complex chemistry initiated around one star can survive the journey to other stellar systems, potentially seeding distant worlds with the molecular foundations of biology. 3I Atlas also serves as a probe of the interstellar medium itself, the space between stars through which it has traveled for eons during its journey. It has been constantly bombarded by cosmic radiation and interstellar dust particles, each impact leaving microscopic traces that tell us about the conditions in regions of space we have never directly explored. The surface composition of the comet's nucleus bears the scars of this long exposure to interstellar conditions, creating a dark, radiation-processed crust that preserves beneath it the pristine ice from its original formation. This layered structure provides a timeline that extends from the present moment all the way back to the epoch when the comet first condensed from the disk around its parent star. As 3I Atlas approaches Mars, the Red Planet's own exploration fleet stands ready to witness this cosmic encounter from a perspective unique in human history. Never before have we possessed multiple sophisticated spacecraft positioned to observe an interstellar visitor during its passage through our inner solar system. The Mars Reconnaissance Orbiter, with its high-resolution cameras and spectrometers, will attempt to detect any changes in the Martian atmosphere that might result from the comet's passage. While such effects are expected to be subtle, the instruments are sensitive enough to detect molecular signatures that might appear as particles from 3 IATLAS, interact with Mars' upper atmospheric layers. More intriguingly, the possibility exists for observable electromagnetic phenomena, as the charged particles streaming from the comet's ionized coma interact with Mars' residual magnetic field, while the red planet lacks the strong global magnetic field that creates Earth's spectacular auroras. It does possess localized magnetic anomalies that could potentially channel interstellar particles in unexpected ways. The ExoMars Trace Gas Orbiter, equipped with cameras designed to capture high-resolution images of the Martian surface, will be scanning for any luminous phenomena that might appear in the planet's thin atmosphere during the period surrounding 3I Atlas. Closest approach these observations could provide the first documented evidence of interstellar material, creating visible effects in a planetary atmosphere. Ground-based telescopes coordinating with the Mars orbiters will simultaneously observe both the comet and the planet, providing crucial context for interpreting any changes or phenomena detected by the spacecraft. This multi-platform approach ensures that any effects can be properly attributed to the comet's influence rather than other factors. The dust streaming from 3I Atlas as it warms creates a tenuous but measurable addition to the population of small particles that already exist throughout our solar system. This interstellar dust carries chemical and isotopic signatures that distinguish it from the native material created by solar system comets and asteroids over the past 4.5 billion years. Some of these dust grains will eventually settle into stable orbits around the Sun, becoming permanent residents of our solar system, though they will remain forever marked by their exotic origin. Future spacecraft traveling through these regions might encounter particles that began their existence around another star. The possibility that some material from 3I Atlas might eventually reach Earth's atmosphere years or decades from now raises fascinating questions about detection and analysis. Meteor showers caused by interstellar dust would create streaks of light in our sky, carrying chemical signatures from another world. Advanced detection systems currently being developed could potentially identify individual meteoric particles of interstellar origin, allowing scientists to collect and study samples of matter from another star system without the impossible expense and technical challenges of interstellar missions. The trajectory analysis of 3I Atlas provides valuable information about the gravitational environment it has encountered during its million-year journey through space. Each close approach to a massive object, whether a star-brown dwarf or rogue planet, leaves subtle signatures in the comet's motion that can be decoded through careful orbital calculations. These gravitational encounters act like a historical record preserved in the comet's current trajectory, telling us about the distribution of massive objects in our local galactic neighborhood and the frequency of close approaches that wandering interstellar objects might experience. The statistical rarity of 3I Atlas trajectory alignment with our solar system's orbital plane continues to intrigue researchers, while such precision is not impossible. The low probability of random alignment has prompted careful analysis of the factors that might influence interstellar object trajectories. One possibility involves the galactic gravitational environment itself. The disk structure of our Milky Way galaxy creates preferential directions for object motion, and the tidal forces from the galactic center might influence the trajectories of objects ejected from star systems in our local neighborhood. Alternatively, selection effects might play a role. We are more likely to detect interstellar objects that pass through the plane of our solar system, where our planets and most of our observational instruments are located. Objects arriving from high inclination angles might be more difficult to spot and track, regardless of the statistical considerations. 3I Atlas represents a remarkable opportunity to study an object that has experienced conditions and environments completely alien to anything in our solar system. The data being collected will inform our understanding of interstellar space, planetary formation, and the chemical evolution of our galaxy. The brightening behavior of 3I Atlas as it approaches perihelion provides insights into the internal structure and composition of interstellar comets, the rate at which it releases gas, and dust suggests a nucleus that may be more porous or volatile rich than typical solar system comets. This enhanced activity could reflect formation conditions around its parent star that differed from those in our own stellar neighborhood. Different stellar masses, temperatures, and chemical compositions could create comets with varying internal structures and volatile content. Spectroscopic analysis continues to reveal new details about the chemical composition of 3IATLAS coma. The detection of unusual molecular species or isotopic ratios could provide clues about stellar nucleosynthesis processes that occurred in its origin system. The organic chemistry occurring in the comet's coma, as solar heating drives increasingly complex reactions between simple molecules, demonstrates that space environments can serve as vast chemical laboratories, creating compounds that might later contribute to the development of life on planets. As October approaches and 3I Atlas prepares for its closest solar approach, the international space science community has mobilized resources on a scale unprecedented for studying a single astronomical object. This coordination represents a new model for how humanity might respond to future discoveries of rare cosmic phenomena. The James Webb Space Telescope continues its detailed spectroscopic monitoring of the comet, providing chemical analysis with unprecedented precision, while the Hubble Space Telescope captures high-resolution images that reveal the structure and evolution of the comet's nucleus and coma. Ground-based observatories around the world have formed networks to ensure continuous monitoring of 3I Atlas as it moves through different regions of sky. This global coordination maximizes the scientific return from what may be a once-in-a-lifetime opportunity. The Parker Solar Probe positioned closer to the Sun than any previous spacecraft will observe. 3I Atlas, during its most active period when solar heating reaches maximum intensity, potentially witnessing dramatic changes in the comet's behavior that have never been observed in any solar system object. The data collected during this comprehensive observation campaign will establish baseline measurements for interstellar comet behavior against which future discoveries can be compared. As detection capabilities improve, we expect to encounter more such visitors, transforming our understanding from individual case studies to statistical populations. The Vera Rubin Observatory, now beginning its systematic survey of the southern sky, promises to revolutionize interstellar object detection with its ability to scan large areas rapidly and repeatedly. This automated approach could discover interstellar visitors months or even years before they reach the inner solar system. Early detection would enable dedicated missions to be planned and launched, allowing spacecraft to rendezvous with interstellar objects while they are still far from the Sun. And relatively inactive, such missions could provide detailed close-up studies of pristine interstellar material. The technological requirements for intercepting high-velocity interstellar objects present significant challenges, but also drive innovation in propulsion systems and spacecraft design. The solutions developed for these missions could have applications for other ambitious space exploration goals. Sample return missions to interstellar objects represent one of the most scientifically valuable but technically challenging goals in planetary exploration. The analysis of physical samples from another star system would provide information about stellar environments and planetary formation processes that cannot be obtained through remote observation alone. The organic molecules detected in 3IATLAS suggest that the chemical building blocks of life may be common throughout our galactic region, carried by wandering objects that connect star systems across vast distances. While we cannot determine whether such objects transport actual living organisms, they certainly distribute the molecular foundations necessary for biology. This cosmic chemistry network implies that the development of life may be influenced by materials and processes that operate on galactic scales, rather than being confined to individual planetary systems. The implications for astrobiology and our search for life beyond Earth are profound. The study of 3I Atlas also provides perspective on the long-term future of our own solar system. Billions of years from now, gravitational interactions with passing stars will eject comets and asteroids from our outer solar system, sending them on interstellar journeys that may eventually bring them to other star systems. In this cosmic perspective, every interstellar visitor serves as both an ambassador from our galactic past and a preview of our solar system's contribution to the ongoing exchange of material between stellar neighborhoods. This exchange process may be fundamental to how galaxies evolve and develop over cosmic time. The gentle gravitational dance that guides 3I Atlas through our solar system operates according to universal physical laws that govern motion throughout the cosmos. The same principles that determine planetary orbits around distant stars control the trajectory of this interstellar wanderer. The chemistry creating the comet's glowing coma follows molecular physics that operates identically in stellar nurseries throughout our galaxy. The spectral lines we observe from 3I-ATLAS correspond to the same atomic and molecular transitions that astronomers use to study the composition of distant stars and nebulae. As this cosmic messenger continues its approach toward Mars, we find ourselves witnessing an event that demonstrates the fundamental interconnectedness of our galactic environment. Star systems are not isolated islands, but participants in a vast network of material and energy exchange. The measurements and observations collected from 3I Atlas will enhance our understanding not just of this individual object, but of the processes that connect planetary systems throughout our region of the galaxy. These insights will guide future missions, inform theoretical models, and expand our perspective on humanity's place in the cosmic order. The approaching Mars encounter represents more than just a scientific milestone. It symbolizes our species' growing capability to study and understand phenomena that operate on galactic scales. As our instruments become more sophisticated, we are beginning to perceive the universe as a dynamic, interconnected system. Whether 3I Atlas poses any meaningful threat to Mars appears increasingly unlikely as observations continue to confirm its behavior as a typical, though remarkably well-preserved interstellar comet. The real significance lies in what this visitor teaches us about the nature of our cosmic environment. The true threat, if we can call it that, may be to our assumptions about the isolation and uniqueness of our solar system. 3I Atlas reminds us that we are part of a galaxy where matter, energy, and potentially even the seeds of life flow freely between star systems across distances that dwarf human comprehension. In the quiet moments before this cosmic encounter, we can appreciate both the rarity of this opportunity and the profound questions it raises about our place in a universe where wandering objects carry messages between distant worlds, connecting us to stellar neighborhoods we may never visit, but whose influence touches our own small corner of the galaxy. As the ancient ice of 3I Atlas continues to warm and sublimate under our sun's gentle heating, it releases not just gas and dust, but possibilities, new ways of understanding how star systems communicate across the vast spaces that separate them. New insights into the chemical processes that may seed worlds with the building blocks of complexity and perhaps life itself. And so we drift onward through this cosmic story, carried by the same gravitational currents that guide 3I Atlas on its remarkable journey from the cold depths between stars to its brief, brilliant encounter with our warm inner solar system, where planets dance and rovers explore, and humanity watches with instruments sensitive enough to detect the whispers of alien chemistry in the approaching hours and days. As 3I-ATLAS sweeps past Mars at 18 million miles distance, we will witness not a threat, but a gift. A cosmic present from the deep galaxy that reminds us we are not alone in space, but part of an ancient network of worlds connected by the patient migration of ice and rock and organic molecules across the light years that separate star from star. The story of 3I Atlas continues to unfold with each observation, each spectrum, each carefully measured change in brightness, and position a story that began billions of years ago in the disk around another sun and reaches its current chapter in our own solar system. where human curiosity meets cosmic wandering in a dance as old as the galaxy itself. The measurements streaming back from observatories around the world paint an increasingly detailed portrait of 3I Atlas as it continues its ancient journey through our solar system. Each data point adds another brushstroke to our understanding of this cosmic wanderer, revealing subtle details that speak to processes occurring billions of years ago around a star we may never identify. Ground-based telescopes equipped with increasingly sensitive detectors have begun mapping the three-dimensional structure of the comet's coma. That glowing envelope of gas and dust that surrounds its solid nucleus like a gossamer shroud. These observations reveal asymmetries and variations that tell us about the rotation and surface properties of an object that has spent eons tumbling through the void between stars. The dust grains streaming away from 3I Atlas carry within their microscopic structures a record of bombardment by cosmic radiation. During the comet's long interstellar voyage, each particle has been sculpted by high-energy impacts that have altered its surface chemistry, creating compounds that exist nowhere else in our solar system. As these grains catch and scatter sunlight, they create spectral signatures that our instruments can decode like reading a book, written in the language of atomic physics. The story they tell speaks of temperatures near absolute zero radiation fields, stronger than anything experienced by objects native to our solar system, and chemical processes that occur only in the depths of interstellar space. The tail of 3I Atlas, now stretching millions of miles behind the comet, as it responds to solar wind pressure, represents more than just a beautiful celestial display. It serves as a real-time laboratory for studying how interstellar material behaves when subjected to the electromagnetic environment of our inner solar system. Particles within this tail follow complex trajectories determined by their size, charge, and composition, creating a natural sorting mechanism that separates different types of material into distinct streams. Astronomers studying these patterns can deduce information about the internal structure of the comet's nucleus and the processes driving its activity. The interaction between 3I Atlas and the solar wind creates phenomena that have never been observed before in any solar system object. The magnetic field lines frozen into the comet during its formation around another star interact with our sun's magnetic field in ways that generate subtle electromagnetic disturbances detectable by sensitive radio telescopes on Earth. These magnetic signatures provide a window into conditions that existed in the stellar nursery, where 3I Atlas was born. Magnetic fields play crucial roles in star and planet formation, and any remnant magnetization in the comet tells us about the magnetic environment of its origin system billions of years ago, as October draws nearer the brightness of 3I Atlas continues to increase at a rate that suggests its nucleus may contain more volatile materials than typical solar system comets. This enhanced activity could indicate that the comet formed in a region of its parent stellar disk, where temperatures were lower or chemical compositions differed from those in our own primordial solar nebula. The specific molecules being released provide clues about the stellar environment where 3I Atlas originated the ratios of different carbon compounds. The presence of exotic sulfur-bearing molecules and the isotopic signatures of noble gases all contribute to a chemical fingerprint that could eventually identify the type of star system from which this wanderer emerged. Spectroscopic observations have detected what appear to be complex organic polymers, molecules consisting of carbon chains and ring structures that form through radiation chemistry. In cold environments, these compounds represent some of the most complex chemistry known to exist in space, and their presence in 3I Atlas suggests that the building blocks of biochemistry may be distributed throughout our galactic neighborhood. The discovery of these organic molecules in an object that has survived millions of years of interstellar travel demonstrates the remarkable stability of certain chemical bonds under extreme conditions. This finding has profound implications for theories about how the ingredients for life might be distributed between star systems. Temperature measurements of different regions of 3IATLAS nucleus reveal variations that suggest an inhomogeneous internal structure. Some areas appear to contain more volatile ices, while others seem dominated by darker, less active materials. These variations might reflect the original accretion process that assembled the comet from smaller particles in its birth system. The rotation period of 3I Atlas, determined from periodic variations in its brightness and gas production, indicates that the comet has maintained structural integrity throughout its long journey. This stability suggests that interstellar objects may be more robust than previously thought capable of surviving. Not just the cold and radiation of deep space, but also the thermal stresses of approaching different stellar environments. As the comet continues its approach toward Mars, mission planners have identified specific times when conditions will be optimal for various types of observations. The geometry of the encounter will allow spacecraft to view 3I Atlas from angles that provide unique perspectives on its nucleus structure and activity patterns. The European Space Agency's Mars Express orbiter will use its high-resolution camera to capture images of 3IATLAS during its closest approach, potentially revealing surface features and activity patterns that cannot be resolved from Earth-based telescopes. These observations could provide our first detailed views of an interstellar object's nucleus. Simultaneously, the ExoMars Trace Gas Orbiter will employ its spectrometers to analyze the chemical composition of gas streaming from the comet, searching for molecular signatures that might indicate unusual chemistry or isotopic ratios that reflect the object's alien origin. Ground-based radio telescopes will monitor for electromagnetic emissions that might result from the interaction of 3IATLAS ionized coma with the interplanetary magnetic field. These observations could reveal how the electrical properties of interstellar comets differ from those of objects born in our solar system. The coordination required for this multi-platform observation campaign represents a new level of international cooperation in space science. Telescopes and spacecraft operated by different agencies and nations are working together to maximize the scientific return from this rare opportunity. Data from the James Webb Space Telescope continues to reveal new details about the molecular composition of 3IATLAS coma. The instrument's unprecedented infrared sensitivity allows it to detect trace species that would be invisible to other observatories, providing the most complete chemical analysis ever performed on an interstellar object. These measurements reveal not just what molecules are present, but also their relative abundances and how they change as the comet warms under solar heating. This temporal evolution provides insights into the layered structure of the nucleus and how different volatile compounds become active at different temperatures. The Hubble Space Telescope, operating in visible wavelengths, provides complementary observations that reveal the physical structure of the coma, and nucleus high-resolution images show jets of material streaming from specific regions of the nucleus, indicating that activity is not uniform across the surface. These jets appear to follow the comet's rotation, creating spiral patterns in the coma that rotate with the nucleus like cosmic pinwheels. The geometry of these patterns allows astronomers to determine the orientation of the comet's spin axis and map the locations of active regions on its surface. Particle detectors aboard various spacecraft throughout the solar system are monitoring for any dust grains from 3I Atlas that might reach their locations, while the comet will not pass close enough to any spacecraft for direct sampling. The possibility exists that some particles might be scattered into unusual trajectories by interactions with other solar system objects. The Parker Solar Probe, currently diving closer to the Sun than any previous spacecraft, will be positioned to observe 3I Atlas during its most active period when solar heating reaches maximum intensity. The probe's instruments, designed to study the solar wind and corona, will instead focus on this interstellar visitor. Observations from Parker could reveal how 3IATLAS behaves under extreme solar heating conditions that no interstellar object has experienced since leaving its birth system billions of years ago. These measurements will test our understanding of how cometary materials respond to intense radiation and particle bombardment. The dust production rate of 3I Atlas has been steadily increasing as it approaches the Sun, creating an expanding cloud of particles that will eventually spread throughout the inner solar system. Some of this material will persist for years or even decades, becoming a permanent, though sparse addition to the population of interplanetary dust. Future spacecraft missions might encounter these interstellar dust grains, providing opportunities to study material from another star system without the enormous technical challenges of interstellar travel. Advanced collection techniques could potentially gather samples for return to Earth, where they could be analyzed in terrestrial laboratories. The trajectory of 3I Atlas through our solar system provides valuable information about the gravitational influences it has experienced during its interstellar journey. Precision tracking reveals subtle deviations that could indicate close encounters with other massive objects during its travels. These gravitational signatures act like breadcrumbs marking the path 3I Atlas has followed through our local galactic neighborhood. Each encounter with a star-brown dwarf or rogue planet leaves traces that can be decoded through careful analysis of the comet's current motion. The statistical analysis of 3I Atlas trajectory continues to puzzle researchers, while the alignment with our solar system's orbital plane is not impossible. It represents such a low probability event that alternative explanations deserve consideration. One possibility involves the influence of our galaxy's gravitational structure. The disk-shaped distribution of stars and dark matter in the Milky Way creates preferential directions for object motion that might influence the trajectories of interstellar wanderers. Alternatively, the apparent coincidence might reflect observational biases. We are more likely to detect and track objects that pass through regions of space where our planets and instruments are concentrated, while objects arriving from other directions might escape notice entirely. Regardless of the statistical considerations, 3I Atlas represents an unprecedented opportunity to study processes and materials that exist nowhere else in our solar system. The chemical and physical data being collected will inform scientific understanding for generations to come. The brightening pattern of 3I Atlas, as it continues toward perihelion, suggests that its nucleus may be undergoing changes that reveal fresh ice beneath a radiation-processed surface layer. This exposure of pristine material provides insights into the original composition of the comet when it first condensed from the disk around its parent star. Temperature modeling indicates that the heat now penetrating into the nucleus is reaching depths that have remained frozen since the comet's formation. Billions of years ago, the sublimation of these ancient ices releases molecules that have been preserved in pristine condition, providing a direct sample of the chemistry that existed in another stellar system. Isotopic analysis of the gas streaming from 3I Atlas reveals subtle variations that could identify the nuclear processes that occurred in its parent star. Different stellar masses and compositions create characteristic isotopic signatures that are preserved in materials that form in their planetary disks. These isotopic fingerprints represent the most direct method available for determining the type of stellar environment where 3I Atlas originated. While we may never identify the specific star, the isotopic ratios can tell us about its mass, temperature, and chemical composition. The organic chemistry occurring in the coma of 3I Atlas as solar heating drives reactions between simple molecules demonstrates that space environments serve as vast laboratories for creating complex compounds. These reactions occur under conditions of temperature, density, and radiation that cannot be replicated in terrestrial facilities. The products of this space chemistry include molecules that may be precursors to biological compounds, suggesting that the fundamental ingredients for life could be created and distributed throughout the galaxy by wandering objects like 3I Atlas. As the comet approaches its encounter with Mars, astronomers are preparing to observe phenomena that have never been documented before. The interaction between an interstellar object and planetary environment could produce effects ranging from subtle atmospheric changes to visible electromagnetic displays. The thin atmosphere of Mars makes it particularly sensitive to external influences. Particles from 3I Atlas could potentially create temporary modifications in atmospheric chemistry that might be detectable by sensitive instruments aboard orbiting spacecraft. The residual magnetic field of Mars, though weak compared to Earth's magnetosphere, could still channel charged particles from the comet's coma, creating localized effects that might appear as auroral glows or electromagnetic disturbances. Ground-based observatories equipped with specialized cameras will monitor Mars for any luminous phenomena that might appear during the period of closest approach. These observations could provide the first documented evidence of interstellar material creating visible effects in a planetary atmosphere. The electromagnetic environment around Mars during 3I Atlas passage will be monitored by radio telescopes sensitive to the subtle signals that might indicate interactions between the comet's charged particles and the planet's magnetic field anomalies. These measurements could reveal new information about how interstellar objects interact with planetary environments, providing insights that apply not just to Mars, but to all worlds that might encounter wandering comets from other star systems. The dust streaming from 3I Atlas will eventually disperse throughout our solar system, becoming part of the permanent inventory of interplanetary particles that create phenomena like zodiacal light and meteor showers. This interstellar material will carry chemical signatures that distinguish it from native solar system dust. Advanced detection methods currently being developed could potentially identify individual meteoric particles of interstellar origin when they eventually reach Earth's atmosphere years or decades from now, allowing scientists to study samples of matter from another star system. The possibility of collecting physical samples from 3I Atlas, either through dedicated missions or by gathering particles from its dust trail, represents one of the most exciting prospects in planetary science. Such samples would provide direct laboratory analysis of materials from another stellar environment. The technological challenges of intercepting a high-velocity interstellar object are substantial but not insurmountable. Advanced propulsion systems and trajectory planning could enable spacecraft to rendezvous with objects like 3I Atlas during their passage through our solar system. Early detection capabilities currently being developed would provide the advanced warning necessary to plan and launch such missions. The Vera Rubin Observatory and other automated survey systems promise to discover interstellar visitors months or years before they reach the inner solar system. Sample return missions to interstellar objects would provide unprecedented insights into stellar environments and planetary formation processes that occurred billions of years ago in distant parts of our galaxy. The scientific value of such samples could justify the enormous technical challenges involved. The study of 3I Atlas also provides perspective on the cosmic processes that connect star systems throughout our galactic neighborhood. The same gravitational interactions that ejected this comet from its birth system will eventually send objects from our own solar system on similar interstellar journeys. In billions of years, comets and asteroids from our outer solar system will be scattered by close encounters with passing stars, beginning their own million-year wanderings through the galaxy. These future ambassadors will carry samples of Earth and its sister planets to distant stellar neighborhoods. This cosmic perspective reveals that star systems are not isolated entities, but participants in a vast network of material exchange that operates on galactic scales. The wandering objects like 3I Atlas serve as messengers carrying information about stellar environments across distances that would require impossible interstellar missions to traverse. The gentle gravitational forces that guide 3I Atlas through our solar system operate according to the same physical principles that govern planetary motion around distant stars. The universal nature of these laws ensures that the lessons learned from studying this interstellar visitor apply throughout the cosmos. The chemistry creating the comet's luminous coma follows molecular physics that operates identically in stellar nurseries throughout our galaxy. The same atomic and molecular processes that we observe in 3I Atlas occur in the formation regions of planetary systems around other stars. As this cosmic wanderer continues its approach toward Mars, we find ourselves witnessing an event that demonstrates the fundamental interconnectedness of our galactic environment. The boundaries between star systems are not barriers, but permeable membranes through which matter and energy flow freely. The measurements and observations being collected from 3I Atlas will enhance our understanding, not just of this remarkable object, but of the processes that connect planetary systems throughout our region of the galaxy. These insights will guide future exploration and expand our perspective on humanity's place in the cosmic order. The approaching encounter with Mars represents more than a scientific milestone. It symbolizes our growing capability to study phenomena that operate on galactic scales as our instruments become more sophisticated. We are beginning to perceive the universe as a dynamic, interconnected system where star systems communicate across vast distances in the quiet hours before dawn. When 3IATLAS is visible through telescopes as a fuzzy patch of light moving slowly against the background stars, we can contemplate the remarkable journey that brought this ancient wanderer to our cosmic doorstep. A journey that began when our own world was young and will continue long after our sun has aged and cooled. The true significance of 3I Atlas may not lie in any immediate effects it might have on Mars or other planets, but in what it represents about the nature of our galactic home, a place where matter and energy, and perhaps even the seeds of life, travel freely between stellar neighborhoods, connecting worlds across impossible distances. As we drift deeper into this cosmic story, we are reminded that we are not observers, standing apart from the universe, but participants in an ancient dance of matter and energy that connects us to stars we cannot see, and worlds we will never visit yet, whose influence touches our own small corner of the galaxy through messengers like 3IATLAS. The story of 3I Atlas unfolds not just through telescope observations and spacecraft measurements, but through the profound questions it raises about the nature of discovery itself. In our modern age, when we encounter something truly extraordinary from beyond our solar system, we bring to bear the full arsenal of human curiosity. Instruments scattered across the globe and throughout space, all focused on understanding a single wandering object. There is something deeply moving about this coordinated effort to study 3I Atlas as it passes through our cosmic neighborhood observatories that normally compete for funding and telescope time have united in common purpose, sharing data and coordinating observations to ensure that no detail is missed, no spectrum goes unrecorded, no opportunity for understanding is lost. The international nature of this scientific collaboration reflects something fundamental about how humanity responds to the truly unknown when faced with phenomena that transcend national boundaries and terrestrial concerns. We instinctively reach across political and cultural divides to pool our knowledge and resources as 3I Atlas continues its journey toward Mars. The data streaming back from our various observation platforms tells an increasingly nuanced story about what happens when objects from one stellar environment encounter the conditions of another. The subtle changes in the comet's behavior as it responds to our sun's heating reveal processes that may be universal throughout the galaxy. The warming of 3I Atlas nucleus has now penetrated deep enough to reach materials that have remained frozen since the comet's original formation. Billions of years ago, the sublimation of these pristine ices releases molecules that provide direct samples of the chemistry that existed around another star when our own solar system was still forming. Spectroscopic analysis reveals not just familiar compounds like water vapor and carbon dioxide, but also more exotic species that form only under the specific conditions found in interstellar space. These molecules have survived a journey measured in millions of years, carrying with them information about environments so alien that we can barely imagine them. The coma surrounding 3I Atlas has now grown to dimensions that dwarf entire planets, stretching across millions of miles of space, yet remaining so tenuous that a person could walk through it without noticing anything more than a slight haze. This gossamer envelope contains more material than many asteroids yet spread so thin that it becomes visible only when backlit by our distant sun. Within this vast coma, particles of dust and ice follow complex trajectories determined by radiation pressure, solar wind, and the subtle gravitational influences of planets millions of miles away. The resulting patterns create a natural laboratory for studying fundamental physics under conditions that cannot be replicated in any earthly facility. The tail of 3A Atlas, now streaming behind it like a cosmic banner, has begun to show structural details that reveal the internal composition of its nucleus. Jets of material emerge from specific regions, creating spiral patterns that rotate with the comet's spin. These features provide astronomers with a map of active areas on the surface, each one corresponding to deposits of different volatile compounds. Temperature mapping of the nucleus shows a complex landscape of hot and cold regions, where different types of ice sublimate at different rates, creating a patchwork of activity that changes as the comet rotates. This thermal geography tells us about the original structure of the object when it first condensed from the disk around its parent star. The organic molecules detected in 3I Atlas coma continue to surprise researchers with their complexity and variety. Some of these compounds appear to be forming through real-time chemistry, as simpler molecules released from the nucleus interact under the influence of solar radiation, creating new species that exist nowhere else in our solar system. This space-based chemistry laboratory operates under conditions of temperature, pressure, and radiation that are impossible to duplicate on Earth. The products of these reactions include potential precursors to biological molecules, suggesting that the building blocks of life may be constantly manufactured and distributed throughout the galaxy by wandering objects like comets. The isotopic signatures found in 3IATLAS provide increasingly detailed information about the nuclear processes that occurred in its parent star. Different elements show characteristic ratios that reflect the mass, temperature, and age of the stellar environment where they were forged. These cosmic fingerprints may eventually allow us to identify not just the general region of the galaxy from which the comet originated, but potentially even the specific stellar association or cluster. As the comet approaches its closest encounter with Mars, the Red Planet's exploration fleet stands ready to document this historic meeting from multiple perspectives. The Mars Reconnaissance Orbiter will use its powerful cameras to search for any visible effects in the Martian atmosphere, while spectrometers analyze the chemical composition of any particles that might interact with the planet's thin air. The ExoMars Trace Gas Orbiter, equipped with instruments designed to detect the faintest molecular signatures in Martian atmosphere, will monitor for any changes that might indicate the presence of interstellar material. These measurements could provide the first direct evidence of how wandering objects from other star systems influence planetary environments. Ground-based telescopes coordinating with the Mars orbiters will simultaneously observe both the comet and the planet, providing crucial context for interpreting any phenomena detected by the spacecraft. This multi-platform approach ensures comprehensive coverage of an event that may not occur again for decades. The electromagnetic environment around Mars during 3IATLAS passage presents unique opportunities for discovery. While the red planet lacks the strong magnetic field that creates Earth's spectacular auroras, it does possess localized magnetic anomalies that could potentially interact with charged particles from the comet's ionized coma. Radio telescopes on Earth will listen for any electromagnetic signatures that might indicate such interactions. These observations could reveal how the electrical properties of interstellar objects differ from those of native solar system bodies, providing insights into the electromagnetic environment of deep space. The dust streaming from 3I Atlas represents more than just debris from a melting nucleus. It serves as a probe of the solar wind and interplanetary magnetic field. As these particles interact with the electromagnetic environment of our inner solar system, they create phenomena that can be observed and analyzed from Earth. Some of this dust will eventually settle into stable orbits around the Sun, becoming permanent though sparse additions to the zodiacal dust cloud that creates the faint glow visible in dark skies before dawn. And after sunset, Future observations of this phenomenon may reveal the subtle contribution of interstellar material. The possibility that particles from 3I Atlas might eventually reach Earth's atmosphere raises intriguing questions about detection and analysis. Meteor showers caused by interstellar dust would create streaks of light carrying chemical signatures from another world. These cosmic fireworks might not occur for years or decades, but when they do, they will provide samples of alien matter. Advanced detection systems currently being developed could potentially identify individual meteoric particles of interstellar origin, allowing scientists to collect and study fragments of another star system without the impossible challenges of interstellar travel. The trajectory analysis of 3I Atlas continues to reveal information about its long journey through space precision tracking, shows subtle variations that indicate gravitational encounters with massive objects during its interstellar wandering. Each such encounter leaves mathematical signatures that can be decoded to reveal the distribution of stars, brown dwarfs, and rogue planets in our local galactic neighborhood. These gravitational breadcrumbs provide a unique form of space archaeology, allowing us to reconstruct the path 3I Atlas has followed through regions of space. We have never directly explored the story, written in its orbital elements, spans millions of years and countless light years of travel. The statistical analysis of the comet's trajectory alignment with our solar system's orbital plane continues to generate discussion among researchers, while such precision is not impossible. The low probability of random alignment suggests that factors beyond pure chance may influence how interstellar objects navigate galactic space. One possibility involves the large-scale structure of our galaxy itself. The disk-shaped distribution of stars and dark matter creates gravitational currents that could preferentially guide objects along certain trajectories, much as ocean currents influence the paths of drifting vessels. Alternatively, selection effects may play a role in our observations. We are naturally more likely to detect and study objects that pass through the plane of our solar system, where our planets and instruments are concentrated, while visitors arriving from high angles might escape notice entirely, regardless of the underlying causes. 3. I-Atlas represents an unprecedented opportunity to study materials and processes that exist nowhere else in our solar system. The chemical and physical data being collected will inform scientific understanding for generations, providing baseline measurements against which future interstellar visitors can be compared. The brightening behavior of 3IA-TLAS, as it continues toward its closest solar approach, suggests increasingly vigorous activity as solar heating penetrates deeper into its nucleus. This enhanced outgassing provides opportunities to study layers of material that have remained frozen since the comet's formation. Temperature models indicate that the thermal wave now propagating into the nucleus is encountering different types of ice at various depths, creating a complex pattern of sublimation that reveals the internal structure of this ancient object. Each layer tells part of the story of how 3I Atlas originally assembled from smaller particles in the disk around its parent star. The gas production rates measured by spectroscopic observations show periodic variations that correspond to the comet's rotation as different regions of the nucleus face the Sun. The resulting changes in activity level provide detailed maps of surface composition and structure. Jets of material streaming from specific locations on the nucleus create spiral patterns in the coma that rotate with the comet, like cosmic pinwheels. The geometry of these features allows astronomers to determine the orientation of the spin axis and identify active regions where volatile ices are concentrated. The James Webb Space Telescope continues its detailed chemical analysis of 3IA-TLAS coma, providing molecular identification with unprecedented precision. The instrument's infrared sensitivity reveals trace species that would be invisible to other observatories, creating the most complete inventory ever compiled of an interstellar object's composition. These measurements show not just which molecules are present, but how their abundances change as the comet warms and different volatile compounds become active at different temperatures. This temporal evolution provides insights into the layered structure that developed during the comet's original formation. Complementary observations from the Hubble Space Telescope, operating in visible wavelengths, reveal the physical structure of the nucleus, and COMA high-resolution images show surface features and activity patterns that cannot be resolved from ground-based telescopes. The combination of chemical and physical data from multiple observatories creates a comprehensive portrait of 3I Atlas that exceeds what could be achieved by any single instrument. This collaborative approach represents a new model for studying rare astronomical phenomena. Particle detectors throughout the solar system are monitoring for any dust grains from 3I Atlas that might reach their locations, while the comet will not pass close enough to any spacecraft for direct encounter. The possibility exists that some particles might follow unexpected trajectories. The Parker Solar Probe, currently making unprecedented close approaches to the Sun, will observe 3I Atlas during its most active period, when solar heating reaches maximum intensity. The probe's instruments designed to study solar wind and coronal physics will instead focus on this. Interstellar visitor observations from Parker could reveal how 3I Atlas behaves under extreme radiation conditions that no interstellar object has experienced since leaving its birth system. The measurements will test our understanding of how cometary materials respond to intense solar heating. The dust production rate of 3I Atlas has steadily increased, creating an expanding cloud that will eventually disperse throughout the inner solar system. This material will persist for years, becoming a sparse but permanent addition to the population of interplanetary particles. Future missions might encounter these interstellar dust grains, providing opportunities to study matter from another star system. Samples collected by advanced techniques could potentially be returned to Earth for detailed laboratory analysis. The coordination required for this comprehensive observation campaign demonstrates humanity's growing capability to respond to rare cosmic phenomena. Observatories and spacecraft operated by different nations and agencies work together to maximize scientific return from this unique opportunity. Data sharing protocols developed for 3I Atlas observations establish precedents for future encounters with interstellar objects. As detection capabilities improve, we expect to discover more such visitors, requiring similar levels of international cooperation. The Vera Rubin Observatory, now beginning systematic surveys, promises to revolutionize our ability to spot cosmic wanderers. Its automated detection systems could identify interstellar objects months or years before they reach the inner solar system, providing time to plan dedicated observation campaigns. Early detection would enable spacecraft missions to intercept interstellar visitors while they are still far from the Sun and relatively inactive. Such encounters would provide detailed studies of pristine interstellar material under conditions closer to those of deep space. The technological challenges of intercepting high-velocity interstellar objects drive innovation in propulsion systems and mission design solutions developed for these ambitious goals could have applications throughout space exploration. Sample return missions to interstellar objects represent the ultimate goal for studying these cosmic messengers. Physical samples analyzed in terrestrial laboratories would provide information about stellar environments that cannot be obtained through remote observation. The organic chemistry detected in 3I Atlas suggests that complex molecules may be common throughout our galactic region, distributed by wandering objects that connect star systems across vast distances. While we cannot determine whether such objects transport living organisms, they certainly carry the molecular building blocks necessary for biology. This distribution network implies that the development of life may be influenced by processes operating on galactic scales, rather than being confined to individual planetary systems. The implications for astrobiology and our search for extraterrestrial life are profound. The study of 3I Atlas provides perspective on the long-term evolution of our own solar system. Billions of years from now, gravitational encounters with passing stars will scatter comets and asteroids from our outer regions, sending them on similar interstellar journeys. Future wanderers from our solar system will carry samples of Earth and its neighboring worlds to distant stellar neighborhoods, continuing the cosmic exchange of materials that connects star systems throughout the galaxy. This perspective reveals that planetary systems are not isolated entities, but participants in scales. Objects like 3i Atlas serve as MESS, a vast network of material transfer that operates over cosmic time engines, carrying information across distances that would require impossible interstellar missions. To traverse the universal nature of physical laws ensures that the processes we observe in 3i Atlas operate throughout the cosmos. Gravitational dynamics, stellar heating, and chemical evolution follow the same principles around distant stars, creating similar phenomena in alien environments. The molecular chemistry occurring in the comet's coma demonstrates reactions that likely occur in stellar formation regions throughout our galaxy. The same atomic processes that create complex organic compounds in 3i Atlas operate in the birth environments of other planetary systems. As this interstellar wanderer approaches its encounter with Mars, we witness an event that illustrates the fundamental connectivity of our galactic neighborhood. Star systems communicate through the patient migration of matter across light years that separate stellar families. The approaching Mars flyby represents more than scientific opportunity. It symbolizes humanity's expanding capability to study galactic-scale phenomena. As our instruments become more sophisticated, we perceive the universe as an interconnected web of matter and energy in the hours before 3i Atlas reaches its closest approach to Mars. Telescopes around the world will focus on this cosmic meeting, documenting an encounter between worlds separated by billions of years and countless light years of space. The measurements collected during this brief period will inform our understanding of how interstellar objects interact with planetary environments, providing insights applicable to worlds throughout the galaxy. These observations expand our knowledge beyond our solar system to encompass processes operating on cosmic scales. The significance of 3i Atlas extends beyond immediate scientific discoveries to encompass what it represents about our place in the galactic community. We are not isolated observers, but participants in ancient networks of material exchange that connect stellar neighborhoods across vast distances through messengers like 3i Atlas. We touch alien worlds and sample distant chemistry without leaving our own cosmic address. The wandering ice and rock carry stories from stellar environments we may never visit yet, whose influence reaches us through patient journeys, measured in geological time. As we continue tracking this remarkable visitor through its passage past Mars and toward its eventual return to interstellar space, we are reminded that the universe operates on scales that dwarf human experience, yet touch our lives through subtle influences we are only beginning to understand. The gentle dance of celestial mechanics that guides 3i Atlas follows rhythms established billions of years ago, when galaxies were young and star formation painted nebulae with colors. We can barely imagine the same forces that ejected this comet from its birth system will eventually carry it beyond our sun's influence in the quiet moments of observation when telescopes track the slow motion of 3i Atlas against background stars. We contemplate connections that span the galaxy and timescales that encompass the entire history of complex chemistry in the cosmos. The story continues to unfold with each spectrum collected. Each image captured, each measurement that adds another detail to our understanding of this cosmic ambassador. The data will outlive the brief passage of 3i Atlas itself, becoming part of humanity's permanent record of contact with truly alien matter. Through the patient work of astronomers and the precision of modern instruments, we transform the ancient ice of a wandering comet into knowledge that expands our perspective on existence itself, connecting us to stellar processes that occurred when the universe was younger and our own world was yet to form. In these moments of scientific discovery, we participate in something larger than individual lives or even civilizations. we join the cosmic conversation that connects matter and energy across space and time, creating understanding that bridges the vast distances between worlds and the eons that separate stellar generations. The approaching encounter with Mars marks not an ending, but a continuation of the story that began when 3I Atlas first condensed from alien stardust, and will continue long after our own sun has aged and cooled, carrying its message to future observers in stellar systems yet to be born. As we approach the culmination of this extraordinary cosmic encounter, the final preparations are underway for what promises to be one of the most comprehensively documented astronomical events in human history. Every available instrument, every sensitive detector, every carefully calibrated spectrometer stands ready to capture the fleeting moments when 3I Atlas sweeps past Mars at its closest approach. The red planet itself has become an unwitting observatory platform, as multiple spacecraft currently exploring its surface and orbiting in its thin atmosphere prepare to turn their attention skyward toward this interstellar visitor. The rovers that normally analyze Martian rocks and soil will pause in their geological investigations to monitor radiation levels and atmospheric conditions during the comet's passage. Curiosity and perseverance, those mechanical explorers that have spent years methodically examining the ancient history preserved in Martian geology, will briefly become sentries, watching for any subtle changes that might indicate the influence of this cosmic wanderer. The instruments designed to search for signs of past life on Mars will instead monitor for the signatures of current activity from an object that carries within its nucleus the chemistry of another world entirely. The orbital mechanics of this encounter create a geometry that astronomers could hardly have designed more perfectly if they had planned it themselves. 3I Atlas will pass Mars at precisely the distance and angle that maximizes observational opportunities while minimizing any risk of interference with ongoing missions. It's as if the universe has conspired to provide the ideal natural laboratory for studying interstellar phenomena. Ground-based observatories have been coordinating their activities for months, ensuring continuous coverage as the comet moves through different regions of sky. The international nature of this effort spans continents and time zones, creating a global network of watchers, all focused on a single point of light that carries messages from the depths of space. The electromagnetic environment around Mars during the encounter presents unique opportunities for discovery that extend far beyond simple visual observation. Radio telescopes sensitive to the faintest signals will monitor for any interactions between the comet's charged particles and Mars' residual magnetic field, while infrared detectors search for thermal signatures that might indicate unexpected heating of the Martian atmosphere. The possibility, however remote, of witnessing auroral phenomena on Mars during 3I Atlas passage has captured the imagination of researchers worldwide. While the red planet lacks the strong global magnetic field that creates Earth's spectacular northern and southern lights, it does possess localized magnetic anomalies that could potentially channel interstellar particles in ways that create brief luminous displays. These potential auroras would be faint and fleeting, visible only to the most sensitive instruments, but they would represent something unprecedented in human experience. The first documented case of interstellar material creating visible effects in the atmosphere of another world. The images, if captured, would become iconic symbols of the cosmic connections that bind star systems together across vast distances. The dust streaming from 3I Atlas, as it continues to warm and outgas, creates another layer of complexity to the encounter. This microscopic debris follows trajectories determined by radiation pressure and gravitational influences, creating patterns that extend millions of miles behind the comet. Some of these particles might interact with Mars' upper atmosphere in ways too subtle for direct detection, but significant enough to alter chemical processes. Atmospheric models suggest that even the tenuous outer reaches of Mars' thin air could experience measurable changes if exposed to the exotic chemistry carried by 3I Atlas. The molecules streaming from this interstellar visitor include compounds that have never existed in our solar system species, formed through processes that occurred around an alien sun, under conditions we can barely imagine the spectrometers aboard Mars. Orbiting spacecraft will search for these molecular signatures with sensitivity measured in parts per billion, looking for chemical fingerprints that would indicate the presence of truly alien matter in the Martian environment. The detection of such signals would provide direct evidence that interstellar objects can influence planetary atmospheres. Temperature monitoring systems designed to track the thermal behavior of Mars' atmosphere will record any anomalies that might correlate with the comet's passage, while significant heating effects are unlikely. The instruments are sensitive enough to detect variations that would be invisible to less sophisticated sensors. The interaction between 3I Atlas and the solar wind creates phenomena that will be observable from multiple vantage points throughout the solar system. As the comet's nucleus continues to sublime under solar heating, it releases charged particles that become part of the complex electromagnetic environment of interplanetary space. These particles carry with them the magnetic signatures of their origin embedded during the comet's formation around another star. When they interact with our sun's magnetic field, they create disturbances that propagate outward like ripples in an invisible pond. Spacecraft positioned throughout the solar system will detect these electromagnetic waves, providing a three-dimensional picture of how interstellar material behaves in our stellar environment. The Parker Solar Probe, currently making its unprecedented close approaches to our Sun, will observe 3I Atlas. From a perspective, no human-made object has ever achieved watching an interstellar visitor during its most active period, when solar heating drives maximum outgassing and particle production. These observations from Parker will reveal how materials from another star system behave under extreme solar conditions, testing our understanding of cometary physics under circumstances that push the boundaries of known science. The data collected could reveal fundamental differences between interstellar and solar system objects that are invisible under less extreme conditions. The coordinated nature of this observation campaign represents a new model for international scientific cooperation. Observatories that normally compete for telescope time and research funding have united in common purpose, sharing data and resources to ensure that no aspect of this encounter goes unobserved. Real-time communication networks connect observatories across multiple continents, allowing researchers to coordinate observations and share preliminary results. As they unfold, this collaborative approach maximizes the scientific return from an event that may not repeat for decades or longer. The data streaming back from these various platforms paints an increasingly detailed picture of 3I Atlas as it approaches its moment of closest encounter with Mars. Each spectrum reveals new details about the chemical composition of this cosmic wanderer, while high-resolution images show the physical structure of its nucleus and the complex patterns within its coma. Temperature measurements indicate that the thermal wave now penetrating deep into the comet's interior is reaching materials that have remained frozen since the object's original formation. Billions of years ago, the sublimation of these pristine ices provides direct samples of the chemistry that existed around another star when our own solar system was still a swirling cloud of gas and dust. The organic molecules detected in increasing abundance as 3I Atlas warms include compounds of staggering complexity, some containing carbon chains and ring structures that approach the threshold of biological chemistry. These molecules represent the most sophisticated chemical processes known to occur naturally in space environments. The presence of such complex organic compounds in an object that has survived millions of years of interstellar travel demonstrates the remarkable stability of certain chemical bonds under the extreme conditions of deep space. This finding has profound implications for understanding how the building blocks of life might be distributed throughout our galaxy. Isotopic analysis continues to reveal subtle signatures that distinguish 3I Atlas from any object native to our solar system. These chemical fingerprints provide clues about the nuclear processes that occurred in the comet's parent star and the environmental conditions that existed in its birth system. The ratios of different isotopes tell a story that spans billions of years from the original stellar nucleosynthesis that created the heavy elements through the planetary formation processes that assembled them into the wandering object. We observe today, each measurement adds another detail to our understanding of stellar evolution and planetary system formation as the critical hours approach. Mission controllers at space agencies around the world are making final adjustments to observation schedules and instrument settings. The goal is to capture every possible detail of an event that represents humanity's most intensive study of an interstellar object. The Mars Reconnaissance Orbiter will use its powerful high-res camera to search for any visible phenomena in the Martian atmosphere, while its spectrometers analyze the chemical composition of the thin air for any traces of interstellar material. The coordination required for these observations demonstrates the precision that modern space science can achieve. Simultaneously, the ExoMars Trace Gas Orbiter will employ its suite of instruments to monitor for electromagnetic effects and atmospheric changes that might indicate interactions between the comet's charged particles and Mars' residual magnetic field. These measurements could provide insights into planetary magnetism and atmospheric physics that extend far beyond this single encounter. Ground-based radio telescopes will listen for the faint electromagnetic signatures that might indicate unusual interactions between three IATLAS and the interplanetary medium. These signals, if detected, would reveal information about the electrical properties of interstellar objects and how they differ from native solar system bodies. The James Webb Space Telescope continues its detailed chemical analysis, providing molecular identification with unprecedented precision as 3I Atlas approaches maximum activity levels near its closest solar approach. The instrument reveals trace species and chemical processes that would be invisible to any other observatory. Complementary observations from Hubble Space Telescope capture high-resolution images that show the physical evolution of the nucleus and coma as solar heating drives increasingly vigorous outgassing. The combination of chemical and physical data creates a comprehensive portrait of an interstellar visitor. The dust production rate has now reached levels that create visible changes in the comet's appearance from night to night, as observers track its progress across the sky. The expanding coma now spans dimensions that dwarf planets, yet remains so tenuous that it would be barely perceptible to human senses at close range. This gossamer envelope contains material that originated around another star, carrying within its microscopic particles the chemical signatures of alien stellar processes. The dust grains themselves have been sculpted by millions of years of cosmic radiation bombardment, creating surface chemistries that exist nowhere else in our solar system. Some of this dust will eventually settle into long-term orbits around our Sun, becoming permanent, those sparse additions to the zodiacal cloud that creates the faint glow visible in dark skies before dawn and after sunset. Future observations of this phenomenon may reveal the subtle contributions of interstellar material to our local space environment. The possibility that particles from 3IATLAS might eventually reach Earth's atmosphere raises fascinating questions about detection and analysis. Meteor showers caused by interstellar dust would create streaks of light carrying chemical signatures from another world. These cosmic fireworks might not appear for years or decades, but when they do, they will provide direct samples of alien matter. Advanced detection systems currently under development could potentially identify individual meteoric particles of interstellar origin, allowing scientists to collect and analyze fragments of another star system without the enormous technical challenges of launching interstellar missions. The trajectory analysis of 3I Atlas reveals information about its journey through space that extends far beyond our solar system. Precision tracking shows gravitational influences from encounters with massive objects during its interstellar wandering, creating a map of the stellar neighborhood through which it has traveled. These gravitational signatures act as cosmic breadcrumbs, marking the path through regions of space that human instruments have never directly explored. Each mathematical deviation in the comet's orbit tells part of the story of its million-year journey through the galaxy. The statistical rarity of 3I Atlas trajectory alignment with our solar system's orbital plane continues to generate scientific discussion. While such precision is not impossible, it represents a sufficiently low probability event to warrant careful analysis of the factors that might influence interstellar object navigation. One explanation involves the large-scale gravitational structure of our galaxy. The disk-shaped distribution of stars and dark matter creates currents and eddies in space-time that could preferentially guide objects along certain trajectories, much as ocean currents influence the paths of drifting vessels on Earth. Alternatively, observational selection effects may influence which interstellar objects we detect and study. We are naturally more likely to notice and track visitors that pass through the plane of our solar system, where our planets and instruments are concentrated, while objects arriving from high inclination angles might escape detection entirely, regardless of the underlying causes. 3I Atlas represents an extraordinary opportunity to study processes and materials that exist nowhere else in our immediate cosmic neighborhood. The chemical and physical data being collected will establish baseline measurements for interstellar object behavior against which future discoveries can be compared. The brightening pattern of 3I Atlas suggests that solar heating is now penetrating to depths within the nucleus that have remained frozen since the comet's formation. This thermal penetration reveals the internal structure developed during the original accretion process, when countless smaller particles combined to form the wandering object we observe today. Jets of material streaming from specific regions of the nucleus create spiral patterns in the expanding coma that rotate with the comet's spin like cosmic pinwheels. The geometry of these features allows astronomers to map the distribution of different volatile compounds across the surface and determine the orientation of the spin axis. The gas production rates show periodic variations corresponding to the comet's rotation, as different regions face the Sun, creating a detailed picture of surface composition and thermal properties. These measurements provide insights into how interstellar objects maintain structural integrity during their long journeys through space. Temperature modeling indicates that the heat now reaching the interior of 3I Atlas is encountering layers of different composition laid down during the comet's original formation. Each layer tells part of the story of conditions in the disk around its parent star billions of years ago. As the final hours before closest approach tick away, the global network of observers makes last-minute preparations for documenting this historic encounter. The coordination required demonstrates humanity's growing capability to respond to rare cosmic phenomena with unprecedented precision and cooperation. The measurements collected during the brief period of closest approach will need to sustain scientific analysis for potentially decades until another interstellar visitor makes such a convenient passage through our inner solar system. The rarity of these encounters makes every data point precious, every spectrum valuable. Beyond the immediate scientific value, 3I Atlas represents something more profound about our place in the galactic community. It serves as a tangible reminder that star systems are not isolated islands, but participants in a vast network of material exchange that operates over cosmic timescales. The wandering ice and rock carry stories from stellar environments we may never visit yet, whose influence reaches us through patient journeys measured in millions of years. The same gravitational forces that ejected this comet from its birth system will eventually scatter objects from our own solar system on similar interstellar odysseys. Future ambassadors from Earth and its neighboring worlds will carry samples of our local chemistry to distant stellar neighborhoods, continuing the cosmic conversation that connects matter and energy across light years and eons. In this perspective, 3I Atlas serves as both messenger from our galactic past and preview of our solar system's contribution to the ongoing exchange of materials between star systems. The gentle dance of celestial mechanics operates according to universal principles that ensure this cosmic dialogue continues across space and time as we prepare to witness the closest approach to Mars. We stand at a unique moment in the history of human knowledge. Never before have we possessed the technological capability to study an interstellar visitor with such comprehensive detail. Never before have we had spacecraft positioned throughout the solar system, ready to observe cosmic phenomena from multiple perspectives. The approaching encounter symbolizes our species, expanding to understand processes that operate on galactic scales as our instruments become more sophisticated. We perceive the universe not as a collection of isolated objects, but as an interconnected web of matter and energy. The gentle warming of ancient ice under our sun's influence releases not just gas and dust, but possibilities, new ways of understanding how chemical complexity arises and spreads throughout the galaxy, new insights into the processes that connect worlds across impossible distances. In the quiet hours before this cosmic meeting, we can appreciate both the rarity of this opportunity and the profound implications it holds for our understanding of existence itself through 3I Atlas. We touch alien chemistry and sample distant stellar processes without leaving our own small corner of the galaxy. The story that began billions of years ago in the disk around another star reaches its current chapter in our solar system, where human curiosity meets cosmic wandering in a dance as ancient as the galaxy itself. The measurements we collect will outlive this brief encounter, becoming part of humanity's permanent record of contact with truly alien matter. As 3I Atlas continues its approach toward Mars, carrying within its nucleus the frozen chemistry of another world, we find ourselves witnesses to an event that connects us directly to the vast community of stars that surrounds us in space and time. The gentle countdown continues as 3I Atlas maintains its course toward this historic rendezvous with Mars. And in these precious final moments before closest approach, we find ourselves contemplating what it truly means to witness such an encounter between worlds, separated not just by distance, but by the vast spans of cosmic time itself. The observations streaming in from our global network of telescopes reveal that 3I-ATLAS is now exhibiting behavior patterns that exceed even the most optimistic predictions of cometary activity. The nucleus appears to be releasing materials at rates that suggest its internal structure may be fundamentally different from anything we've encountered in our native solar system, creating opportunities for discovery that extend far beyond what anyone initially anticipated. Spectroscopic analysis shows that as solar heating penetrates deeper into the comet's core, it's encountering reservoirs of volatile compounds that have remained pristine since the object's formation around its alien parent star. These ancient ices carry molecular signatures that speak to stellar chemistry processes occurring under conditions that may have been quite different from those in our own primordial solar nebula. The complexity of organic molecules now streaming from 3I Atlas has reached levels that approach what we might expect to find in the most chemically active regions of star-forming nebulae throughout our galaxy. These carbon-bearing compounds represent some of the most sophisticated natural chemistry known to occur in space environments, suggesting that the building blocks of biological complexity may be far more widely distributed than we previously imagined. As the comet's coma continues expanding under solar influence, it now spans dimensions that would encompass several Earth diameters. Yet this vast envelope remains so tenuous that its total mass equals only a small asteroid. The gossamer nature of this interstellar cloud demonstrates how efficiently space environments can distribute matter across enormous volumes, creating phenomena visible across millions of miles, yet barely substantial enough to affect a spacecraft passing through. The dust grains within this expanding envelope follow trajectories that create natural experiments in celestial mechanics, as radiation pressure and gravitational influences sort particles by size, composition, and electrical charge. The resulting patterns provide insights into fundamental physics processes that operate throughout the cosmos. Wherever matter interacts with stellar radiation and magnetic fields, temperature measurements indicate that 3I Atlas is now warm enough for the most volatile compounds in its nucleus to begin sublimating substances that remain frozen even in the outer reaches of our solar system are starting to contribute to the comet's activity creating chemical signatures that have never been observed in any object native to our stellar neighborhood. The electromagnetic environment around the comet has become increasingly complex as charged particles from its ionized coma interact with the solar wind and interplanetary magnetic field. These interactions create disturbances that propagate outward through space, like ripples in an invisible ocean carrying information about the electrical properties of interstellar matter radio. Telescopes monitoring these electromagnetic phenomena detect signals that suggest 3I Atlas may possess remnant magnetic fields frozen into its nucleus during formation around its parent star. These ancient magnetic signatures, if confirmed, would provide unprecedented insights into the stellar environment, where this cosmic wanderer originated billions of years ago. And so, as our cosmic journey draws to its gentle close, we find ourselves forever changed by this encounter with 3I Atlas, this ancient wanderer from the depths between stars that has reminded us we are not alone in the vast galactic ocean, but part of something infinitely larger and more connected than we ever dared imagine. Whether threat or gift, this interstellar messenger has shown us that the universe speaks in whispers of chemistry and light, carrying stories across impossible distances to those patient enough to listen. Sweet dreams, fellow travelers, and may your rest be filled with visions of distant suns and the quiet knowledge that somewhere in the darkness, ice and rock and starlight continue their eternal dance. Connecting worlds will never see to the small blue planet we call home. Connecting worlds will never see to the small blue planet we call home.